So what we're going to do in this video is we're going to look at the intersection of two planes. So two options when planes are existing is that they either simply do not intersect or that they do intersect. And if they don't intersect, that means they must be parallel. So one entirely on top of the other one and they never meet. The other option technically would be that they are simply the same plane and therefore they're not intersecting because they are just simply the same equation, they're the same plane, they're representing the same space. The other option being that they intersect. And now when two planes intersect, it's quite hard to see on the diagram I've drawn because it's quite difficult to draw that on 2 dimensions, is that they will intersect at a line. Now that we know how to calculate the equation of a line in general, we can start worrying about that. But what I'll do, if you see here, more 3-dimensional look at it, if you think of that sheet, that part of the book as one plane and this part of the book as another plane, we can see that when two planes meet, they meet at a line. So hopefully that's a better way of showing it in 3 dimensions. So when we find the equation of the line of intersection, we've got two planes, x minus 2y plus 3z equals 1, and 2x plus y plus z equals negative 3. What I can do is simply state a value for one of the variables. So I'm going to let z equal 0. And then from that I'll be able to calculate the values of x and y at that point of z. And from that I'll be able to calculate that gives me a point on the line, and then from that I can get the equation of the line. So as you can see there, that I've been able to calculate based on z equals 0 what x and y are, giving me a single point of intersection as -1, -1, 0. Okay, so now if you think about what we need for the equation of a line, we need to have a normal to the line, and we need to have a point on the line, which we've just got. Okay, so what we can actually do is using the cross product and the normals to the planes, we can then calculate what the cross product is of those normals, which is in fact the normal to the line. Okay, so I'm just going to get another pen because that blue one's running out. So yeah, what I'm just going to do is, like I just said, calculate the normals of the planes, and from that the cross products of the normals, and that will give me the normal to the plane. Okay? So there, what I did after noticing my mistake is I did the cross product of the normals, giving me negative 5i plus 5j plus 5k. And I've skipped some lines to work it out there, but we know how to do the cross product now. And then I've simplified that because cross products, I've just made it, because it's a scalar, why have some 5's. I can take a common factor of 5 because it's just going to make my equation easier to deal with. Because a vector is just dependent on the size. But the whole point of the normal vector is it's just any normal vector. So it doesn't matter what the size of it. Okay? So now what I've got is I've got a point of intersection, sorry, a point on the line, and I've got normal to the line, which means I now can use that to calculate what the equation of the line is. So there I've read off that the normal is negative 1, 1, 1, which are the denominators of the numerator of the fractions of the symmetric form. And then the point on the line is negative 1, negative 1, 0, which I've just put in. And then, so as much as the first function is correct, a better way or a more neat way of saying it is you don't really have to have a denominator dividing by 1, and you don't need to have a 0 in a final answer. So I've just rewritten it without all of that. So, sorry, that is the intersection of two planes.